Okay. Questions about the electrophilic aromatic substitutions? And there's quite a bit of stuff in that section. No questions? None. Okay. What's the product of that reaction? Yeah.
It's a ring.
Okay, write that on your board. Okay. 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 And when you erase, you could probably just erase the group because we're going to be using the benzene rings the entire time. You're just going to be putting different groups on it. Okay. Okay. What? Hold it. Hold it, Alex. No.
What?
No. You got to change one letter. Let me see yours. No. Okay. 2 or 3. Okay. 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 So then maybe red. Maybe people read. At least the first part. So for a benzene ring then, what we really need to know is we need to know what E plus we make from that set of reagents. So HNO3 H2SO4 makes an NO2 plus, then adds into the ring and does substitution. So that's going to substitute for any hydrogen you would like. The other basic ones are, and you need to be able to go both ways in this, so you need to be able to write the product as well as to give the reagents. So for instance, if I took Br2 and FeBr3, what electrophile do I make there? A Br plus. And the same thing would be true for a Cl2 plus an FeCl3. Also, you can use AlCl3 or AlBr3, and that would generate your Cl plus. And then the only other initial one that there is to take SO3 and react it with H2SO4, and there you make an SO3H plus. So in other words, if I was to do that with a benzene ring, which we'll write here, which I'll write to take a benzene ring and we'll do that reaction. So I'll just do that over here. Take the benzene ring, add SO3, H2SO4. We're going to add an SO3H group to the ring. That's going to look like this. That's looking pretty similar to what reagent that we used last week. It looks like a tosyl ester or the precursor to a tosyl ester, but remember what we did was to make the tosylate ester we used this tosyl chloride. So how would I go from this? This is called a sulfonic. This is a sulfonic acid. So how would I go from the sulfonic acid to the tosyl, well, what's almost a tosyl chloride? It's missing the methyl group at the para position. But what reagent would I use? I'd use SOCl2. Because remember, what is the purpose of SOCl2? Well, SOCl2 is to convert an OH into a Cl. So in this case, that's what I'm doing. Now, the role of the tosylate would be to turn the alcohol into a good leaving group, or turn the OH into a leaving group as a chloride. But we can use SOCl2 to convert any OH group into a Cl. So this is where tosyl chlorides come from, or where tosyl chlorides come from. They come from the sulfonic acid, and they come from the sulfonic acid by taking benzene and adding SO3 and H2SO4. The only difference here is that there needs to be a methyl group there, and so what we need to do is we need to work our way up through the possibilities. So all these are just added to a single benzene ring. So they can go anywhere. The groups can go on any of the carbons because they're all hydrogens. All right, let's see, I got a couple more here. What would be the product of that reaction? Write that on your board. Okay. Okay. Almost. You're missing a carbon. So any method you can use to generate an E plus, or in this case a carbocation, anything that you can use, any method you can use, that carbocation will then add to the benzene ring. So in this case, the H plus will not react with the benzene ring, the alkene will not react with the benzene ring because they're both nucleophiles. So what am I going to do? I'm going to add the H plus to the alkene. How's the H plus going to add? By what kind of addition? In other words, where's the H plus going to go? Is the H plus going to go on A or is it going to go on B? A, because that's starts with M. Markovnikov addition. So what I'm going to end up doing is forming a tertiary butyl carbocation. Then the tertiary butyl carbocation is going to end up adding to the ring so that I will end up with a terse butyl group now attached to the benzene ring. So any method you can use to generate a carbocation is going to cause that, it's going to allow that carbocation to then react with the benzene ring. The preferred method would be to take something like an alkyl chloride or an alkyl bromide and react it with either FeCl3 or AlCl3. AlCl3 is that's the preferred reagent. So this is your Friedel-Crafts, and crafts with a C, not a K like the cheese. So Friedel-Crafts, this would be Friedel-Crafts Alkylation. When you take an alkyl halide and react it with the aluminum trichloride, or it could be iron trichloride as well. So if I did this reaction, what would be the major product? Okay. 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 Although yeah, you're okay. 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 No chloride. Because the aluminum is going to take The aluminum is going to take the chloride off and leave you with the carbocation that then is going to add to the ring. So there won't be any chloride in the final product. The name of this Friedel-Crafts Alkylation means I'm adding an alkyl group to the benzene ring. You're changing your answer? Those were the two answers that I saw. Or I saw no answer. So these were the two that I saw. So which one is it? Top or bottom? Why? Yeah. So the aluminum is going to come and grab the chlorine off of the propyl group in this case. Now the issue here is, yeah, if it does that, then I'm going to end up with a primary carbocation. And so if I did end up with a primary carbocation, it would add to the benzene ring. But instead, what's going to happen? With any straight-chained alkyl halide greater than or equal to 3 carbons, you're not going to be able to add that straight chain directly to the ring, because what's going to happen is, as the aluminum pulls the chloride off, this hydrogen is going to shift over, and so we're going to basically have a carbocation rearrangement. So the hydrogen is going to shift over as a hydride shift, then the chloride's going to leave. So I'm not going to form the primary carbocation. Instead, I'm going to form the secondary carbocation. And so in the secondary carbocation case, then that's going to add to the benzene ring. So that isopropyl benzene is the major product. The straight-chained propyl benzene is not. This is not going to be formed. Okay, so you have to remember that you're going to have the possibility of rearrangements with this Friedel-Crafts alkylation. Okay, so you cannot add a straight-chained alkyl benzene or straight-chained alkyl group to the benzene, because it will always rearrange. Okay. The other methyl group. Right, so this hydrogen right here is this one as it moves over to this carbon, and then the chlorine leaves. Let me rewrite it. So what happens is that basically, if I wrote the arrows, it would look like this. The carbon-chlorine bond's going to break, and the chloride's going to go to the aluminum. Then at the same time, this hydrogen is going to do a shift there, so that the carbocation goes there, and then the hydrogen gets shifted over, and then we have AlCl4 minus. So this becomes the methyl group, and then that's what's going to end up adding into the benzene ring. Now, usually when we do this, you might be thinking, then how would you take ethyl chloride and react it with aluminum trichloride and the benzene ring? And if I do this reaction, I'm going to end up with ethyl benzene. So how do you do this reaction and not end up with a primary carbocation? Right? Because there's no rearrangement possible for this reaction. So how do you end up with that primary carbocation? And the answer is, you really don't end up with the primary carbocation, because what happens is that basically, if I write the transition state for this, I'm going to break the carbon-chlorine bond and form the aluminum-chlorine bond at the same time. So what happens is that as the aluminum pulls the chlorine off, this carbon is going to get more and more delta positive. There's going to be a point at which that carbon is delta positive enough to then add into the benzene ring. And it's a little bit short of a full positive ones charge. So the ethyl group will become as positive as it can get, or as positive as it needs to be, to then add to the benzene ring. And that is not quite a full-blown positive one charge. So in this case, we never really form an ethyl carbocation, but we form an ethyl with enough delta positive so that then this can, I don't have people, then you can add the ethyl group into the ring. And the methyl group would be an even worse situation, right? Because then you have a methyl carbocation. So we never really truly form a carbocation. We just have it draw enough electron density away to make this just delta positive enough to add into the ring. Now you might say, well, why doesn't that happen with the propyl group? Because at some point, since this can undergo hydride shift, before you get enough delta positive charge to add to the ring, the hydride is just going to shift over, and you're going to make the full-blown secondary carbocation, which is stable. And then that's going to add into the benzene ring. So Friedel-Crafts alkylations with an alkyl halide and aluminum trichloride can undergo rearrangements to give the major product. I will have to tell you when to rearrange it, although I will not tell you if it's a straight chained alkyl halide that you need to rearrange it, because you need to remember that. But for other ones, I might tell you, I might tell you. So let me go back to let me go back and give you another reaction. So then for this reaction, what would be the major product? With rearrangement. So this does rearrange. What would be its major product? Okay. You're missing a carbon. There's a fourth carbon. Okay. Okay. So as the carbon-chlorine bond breaks and the chloride goes to the aluminum, this hydrogen then shifts over, and I end up then with another tertiary butyl carbocation, and so that's going to add to the benzene ring. Now, in the last class, when we first started in Organic 1 this summer, when we started to talk about carbocation rearrangements, one of the issues that we have is we just don't know when they occur, and if they occur 100% of the time. Bless you. That's why on an exam I'll either tell you that you have to do a rearrangement, or you can do a rearrangement on your own, I guess, but you need to kind of tell me, hey, I rearranged this. It has to follow the proper rules, which number one is you only get one rearrangement per reaction. So it's not like the plus charge can go down the chain until it finds some place to look at, or some place where it feels comfortable, because you get one shift, and it has to form a more stable carbocation. Those are the two rules. And so when we started talking about this, I sort of gave you an example. I know this one occurs. And the reason I know this occurs because when I was teaching at The Ohio University for 1 year, which is probably good enough, in lab, we were doing this electrophilic aromatic substitution reaction, but we were using iron tribromide, and I went to the stockroom and I accidentally got isobutyl chloride instead of terse butyl chloride. So about halfway through the lab, a young scholar came up and said, "Hey, we're using isobutyl chloride and not terse butyl chloride. Does that mean that we have to start all over again?" And I said, "No, you're going to get the same product." And they just didn't accept my answer. They were like, "Well, how does that happen?" And I said, "Well, good. That makes a good post-lab question for you to answer as to how that happens." And this was the answer to the post-lab question, that it underwent a hydride shift. And we added a T-butyl group to the ring. So this is one that actually does occur, and I can attest that it did occur. So that, not all the time are we sure that they would occur. That's why on paper I kind of have to tell you. But this one does. If you do this reaction, you only get terse butyl benzene. So for Friedel-Crafts Alkylation, number one, the name says it all. You're adding an alkyl group to the benzene ring. We need to basically use the aluminum trichloride to pull off the chlorine to make the carbocation, which then will add to the benzene ring. This can undergo rearrangements. And if no matter what straight chained alkyl halide I use, it will always rearrange. So that in this case, the hydrogen on carbon 2 will shift, and I'm going to make a secondary carbocation here from the butyl group. And so I never make a straight chained alkyl benzene using Friedel-Crafts. Right. So if I'm numbering these, it's always going to be 1 through whatever. The carbon 2 hydrogen is always going to do a shift. as the chlorine leaves, so that you end up with a carbocation on carbon 2. It's always going to shift to that carbon. So this is an issue in terms of making straight-chained alkyl benzenes. We can't use Friedel-Crafts alkylation in order to do this because that alkyl group will always rearrange. And then any other alkyl group might rearrange as well, following the rules. One shift to form the most stable carbocation, or more stable carbocation. Okay? So how do we overcome that? How do we overcome this issue of trying to make the straight chain benzene? So if I said I want to go from that benzene to just make a propylbenzene, how would I do that? I can't do it in one step. I've got to use multiple steps. The first step is actually going to be to make what's called the phenyl ketone. So when benzene ring is a substituent, it changes its name from benzene to phenyl. So this is a phenyl ketone. So if I can make the phenyl ketone, I can then do a reduction to turn the carbonyl into a CH2 group. So this is kind of an alternative route to the alkyl benzenes. So what would I use to put this group on the benzene ring? I need a carbocation. The only thing I can add to the benzene rings is a C+. So that means I basically need this. Those of you from lab, this is an acyl carbocation, because it actually has resonance structure. So I can bring the pair of electrons down from the oxygen, make a CO triple bond with the plus charge on the oxygen, so it's stabilized. But how would I make that carbocation? No, I'm going to use a Friedel-Crafts method. So what did I do with Friedel-Crafts? I used aluminum trichloride to pull off a chlorine to make the carbocation. So now I just have to say, oh, all right, well then why don't I just do this and react that, put a chlorine on the carbonyl. The aluminum trichloride will take that off, make the carbocation, and then the carbocation would add to the ring. And this would then be called a Friedel-Crafts acylation reaction because I'm adding an acyl group, which is a C double bond O with a positive charge. I think we called that an aselenium ion in lab. So the idea here is that Friedel-Crafts means you're using aluminum trichloride. That's the traditional Friedel-Crafts reagent, although it can be modified to be either iron chloride or iron bromide. I find those easier to use because in lab, aluminum trichloride, I don't know if it's gone bad or not. Aluminum trichloride reacts with moisture in the air and it basically kills it. For iron, if it's iron 3, then iron bromide, FeBr3 is like a purple color, and FeBr3 that's been killed with water is a yellow color. So basically I know when I've got good FeBr3 because it's nice and purple. And usually that means the bottle, when I open up the bottle, there's about a 2-inch layer of yellow stuff on top that I've got to mine the purple stuff from down below. And I know when it's gone bad. So when I put it in the lab and people don't put the caps back on the bottles, then it starts to turn yellow, and then I know what's good and what's bad. But aluminum trichloride, you can't tell that, but that was a traditional Friedel-Crafts reagent. But Friedel-Crafts, all you need to do is just put a chlorine in something, the aluminum will rip the chlorine off, make the carbocation, and then the carbocation will add to the ring. So in this case, I'm going to use this, which is a carboxylic acid chloride, is what its name is, and we'll start talking about those carboxylic acid derivatives next week. But I do have another question here. Should be an easy question. My acid chloride then, I can make an acid chloride out of any carboxylic acid. How? Because what's its role? To turn OHs into CLs. So SOCl2 has one role. It's got one purpose, but we can use it in a bunch of different methods. So in this case, all I have to do is get my carboxylic acid that I want to add to the benzene ring, convert it to an acid chloride, and do Friedel-Crafts acylation, and sure enough, I will make this phenylketone. Now, once I make that phenylketone, then the question is, how do I reduce the C double bond O, not to a COH, but all the way down to a CH2? And there's probably some alternative methods here, but there's two primary ones that we use for this. And this is the way I present it, so I'm not quite sure that the book takes it in this order. But these are reductions of phenylketones. And so one of these is what's called Clemmensen Reduction. And Clemmensen Reduction, you use mercury and zinc, HCl, and heat. So Clemmensen Reduction are those three reagents. So what you do is you react the mercury with zinc metal to make an amalgam, which once you mix mercury with other metals, it no longer takes on the hazardous properties of mercury. In the old days, before ceramic fillings, they put mercury amalgams in your teeth. Whether that's a wise thing to do or not, that's how they used to do it. So if you have a little neurological damage, or you've gone a little mad like the Hatter in Alice in Wonderland, that's probably the reason why. So that's Clemmensen reduction. And so you need to know, you don't necessarily need to know Clemmensen, although I'll say Clemmensen, but you do need to know the reagents. It is not an appropriate substitute to say Clemmensen without the reagents. That will not get you full credit. You have to know the reagents. So that's one method that will completely reduce carbonyl. The other is what's called the Wolff-Kishner. The Wolff-Kishner reduction. And in the Wolff-Kishner reduction, we react the ketone with what's called hydrazine and KOH and heat. So these are the two methods to reduce a phenyl ketone down to an alkyl benzene. They were developed specifically for that, or they're used specifically for those reductions. And so these two methods then allow us to make straight-chained alkyl benzenes, because Friedel-Crafts will not work because they rearrange. And then once I put the alkyl group on the ring, then I can go back to yesterday and I can do all the reactions on the side chains to put a bromine there, or put a double bond there, or put an epoxide there. But in order to get to that point from benzene, I need to add the straight chained alkyl group. And so these two steps are how you do that. Okay. So let's see. So the idea here is we need a toolbox. We need a toolbox. We need a bunch of reactions that we can use to add groups to the benzene ring. And so these are the ones that we use a lot. Once I do this, then there's going to be other methods that I can use to put things on the side chain, but this comes first. So there are other groups that I need to figure out how to add to the benzene ring. How do I add a carboxylic acid group to the ring? I've got two choices. Can't do it in one. Nope, can't do it in one step right now. Maybe Wednesday. Maybe after tomorrow. There might be a method to do this, but it's actually an industrial method, so it wouldn't work in the lab. But this isn't a one-step reaction. So I'll help you out. I can get there by taking a bromobenzene and doing a reaction or two reactions. I can add a carboxylic acid group to the ring, or I can take a alkyl benzene and also do a reaction to convert that alkyl benzene to a carboxylic acid. And then I just need to know how to add the bromine or the R group, the alkyl group, to the benzene ring. So, which one do you want to do? Your choice. Okay, what do you want to do? How do you want to do it? Oh, you thought I was.
Okay, guys, you can answer to some of it.
Sure.
So we do first add the alkyl.
Not Clemmensen. I'd take my alkyl halide with aluminum trichloride. So I'm going to do Friedel-Crafts. Give me an example. Yep. So I can put an alkyl group on the ring using Clemmensen, or sorry, now you got me doing it. Using Friedel-Crafts, there's too many names. Using Friedel-Crafts, and then I can do the oxidation of the alkyl benzene with KMNO4 or chromium 6 or any of those strong oxidizers. The most common of which is KMNO4. Right. And for those of you in lab, that's what we're going to do tomorrow. We're going to take one of our methyl groups that's attached to the benzene ring, and we're going to use KMNO4, and we're going to oxidize it to a carboxylic acid. So that's one way to do this reaction. Does it matter what the alkyl group is? No, any group gives benzoic acid. So it doesn't matter up here. You could say, well, you know, what's the R? The R can be anything, because once I put it on, it's gone to a carboxylic acid. So that's one way to make the carboxylic acid, is by oxidizing an alkyl group. Now the bromine, how do I convert the bromine to the carboxylic acid? I will give you a hint. Step number 1 is to use magnesium metal to make the what's that reagent called? The Grignard. And then what do I add to a Grignard to make a carboxylic acid? Let me do that again. What did I add? What did I circle in red? CO2. And then step 3, then H plus. So another way to make a carboxylic acid would be to convert the benzene to bromobenzene by using Br2 and like FeBr3 or AlBr3. Then take the bromobenzene, turn it into a Grignard, react it with CO2, and then I get the carboxylic acid. And there are more creative ways I guess we could use, but those two will be sufficient. Okay. So if you're making flashcards, hopefully you have a decent stack, because all of these reactions you're going to need to know not only what the product is, but you're going to have to remember the reactant. Because when we're all said and done today, I'm going to give you a benzene ring, and I'm going to give you another benzene ring with a couple of groups on it. I'm going to say, how do you go from here to here? Right. But what I want to do now is to build up our reaction set so that we can add those groups. So that when you look at it, you go, well, this is how I add this group, this is how I add this group. And the order is going to matter, so the first step is just being able to add the two groups. Okay. All right, so that's how we add a carboxylic acid. Well, let's think of one more here. Okay, I made the carboxylic acid. What can I turn the carboxylic acid into? Well, I could convert it into a CH2OH. So in other words, I could convert that into an alcohol if I wanted to. And then I could convert that alcohol into an aldehyde. So I need two reagents to do this. Your choice. There is an easier one and a harder one, although they're both fairly easy. Kaylee?
For the second step,
So I want to go from a primary alcohol to an aldehyde. I have one reagent right now that'll do that. PCC. Now there's two others that actually will come into play tomorrow and Thursday, called Swern and Desmartin. The Swern and Desmartin are environmentally friendly versions of PCC because PCC involves the chromium-6. But remember, PCC is a poisoned chromium, so that it only stops at the aldehyde. Okay. What would be the first reagent that I would need, though? I want to take a carboxylic acid all the way down to a primary alcohol. I need a really strong reducing reagent. Yep. So the lithium aluminum hydride is our strongest reagent. It will reduce the carboxylic acid all the way down to the primary alcohol. So once you have the carboxylic acid, you can put an aldehyde or a carboxylic acid or an alcohol on there. Let's see. Other groups to add on to the ring. We want to convert sometimes the benzene ring. I would like to add an NH2 group to the ring. I cannot do that in one step. So what I have to do is I've got to convert the ring to nitrobenzene and then convert the nitrobenzene by reduction to the amine. Now, this reaction, if you look in the reading schedule, I take a quick jump to somewhere in chapter 20 something, because this is an amine reaction, and actually the reagents I'm going to show you are amine reagents, and that's where they are in the amine chapter. You don't have to do the problems in the amine chapter, but that's where this content is. That's where the description is in the book. So first of all, I add the nitro group with HNO3 H2SO4. That's going to add on my nitro group, and then to reduce the nitro group, I have a couple of choices. I can use iron metal or tin metal and HCl. So iron, tin, and HCl. And that will reduce the nitro group to an NH2 group. Again, reduction because I'm adding hydrogen, losing oxygen. So this is a reduction. So if you want to add an NH2 group to the ring, you need to put a nitro group on and reduce it with iron or tin. I know, and if you feel like your head's about to explode, hopefully it stretches a little bit before it does. There's only so much you can do as a headless torso. So now I've added my NH2 group. There's other things I'd love to add. I'd love to add an OH. I'd like to add a fluorine. So how do I do that? Well, those are going to involve, first of all, putting on the NH2 group. So once I put the NH2 group on, that's going to be the gateway to get me to adding OH, and iodine, and fluorine. So first of all, once I have my NH2 group, which how did I make it? Nitro, reduction to amine. I'm then going to react this with sodium nitrite. Okay, it's not nitrate, it's nitrite. So sodium nitrite and HCl. And what I'm going to make is what's called a diazonium salt. So I end up adding a second nitrogen to this, and so there's an N triple bond N and the middle nitrogen has a positive charge on it. I can write a resonance structure of this, which I'll actually do in a minute. But this is called a diazonium salt. And in today's folder, in the way I organized it, there's both for most every sort of video lecture there is. If I use PowerPoints, there's a PowerPoint that goes with this. There's actually a PowerPoint for all the stuff I'm doing. I'm just doing it freehand. The Cl minus is the counter ion for the N plus.
Is it attached or is it just like?
It's like kind of like a counter ion, so it's just kind of there. It's like Na plus Cl minus.
Okay.
It's the counter ion. So instead of me just like leaving it off and then you would say, well, where'd the chlorine go? It's just a counter ion. So this diazonium salt then, with a benzene ring attached to it, because remember, that circle means alternating double bonds. That triple bond is now in conjugation with the ring, and it makes it stable. So when you make an aryl diazonium salt, you don't have to worry about it blowing up on you. If you want to make an alkyl diazonium salt, do it in a hood and manipulate with the hands you don't write with, because you never know. That's not stable. So most times if we're going to make a diazonium salt, we're going to make it with an aryl, with a benzene ring, because it's stable. So once I have this diazonium salt, I can do lots of things with it. But how did I get there? I took a benzene ring, added a nitro group, reduced it to an NH2, converted it to the diazonium. So to add any of the next groups, those first three steps have to come first. So I now have my diazonium salt. You want to convert that to an OH. So in other words, I want to add an OH group to the ring. I'm going to add H3O+. Okay, so if I add H3O+ to a diazonium salt, I make what's called a phenol. If you want to convert this diazonium salt to a fluoride, you're going to use NaBF. Oh no, it's H. You're going to use HBF2, I think. Or maybe HBF3. If you want to add an iodine, you just either use potassium iodide or sodium iodide. There's actually more reagents than that to add an iodine, and they're pretty ugly. You should get iodine everywhere. If you want to add, actually, so I think we'll leave it at that. We'll leave it at that at the moment. So the most important of these is the OH. That's a good question. It's kind of an in-between 2 or 3. Or NI. Or NI. NAI. And I reserve the right to change the HBF 3 or 2. The other 2 I'm confident of. Now there's a couple other groups that I would really like to add. So again, starting with my diazonium salt, I'd like to add a C triple bond N, and I would also like to have another method to add either a chlorine or a bromine to the ring. These reagents fall under these are called Meyer reactions. Because the way to do this is to add a copper salt, a copper 1 salt. So in other words, copper cyanide or copper chloride or copper bromide. So if you use a copper salt with the diazonium salt, you'll end up adding the C triple bond N or the Cl or Br. And you might say, we already know how to add chlorines and bromines. I agree. This is another method. We do not know how to add C triple bond N. This is the way you add C triple bond N, is by using copper cyanide and the diazonium salt. And so the reaction of diazonium salt with copper is called Meyer. It's called a Meyer reaction. So at this point, we've built up a pretty big collection of reactions. To add to the benzene ring. And so, that's a page of reactions. We're just starting with benzene. It's like 12, it's like the whole clock of arrows that come out of it, sort of in the pinwheel. But we have to know these. But right now it's pretty boring, because all I've added these things to is a benzene ring. That's boring. So our next step is, once I add one group to the benzene ring, I need to add another. But if I add another group to the benzene ring, where is that group going to go? Is it going to go 1, 2, 1, 3, or 1, 4? And if this was just random, we would say it's random and we'd move on. But of course, it's not random. And so we have to figure out two things that happen when you put a group on a benzene ring. When I put a group on a benzene ring, it's going to affect it two ways. What are those two ways? That group's going to make the benzene react faster or slower. So in other words, that group's going to either increase or decrease the rate of reaction of the benzene ring in electrophilic aromatic substitution. And secondly, that group is going to direct. It's going to direct the second E plus to its position on the ring. And so that group's either going to direct the E plus to go ortho or para, or ortho and para, or it's going to direct the group to go meta to itself. So those two issues, those are the two things that a group, once it's attached to the benzene ring, will affect: the rate and the direction. And so then what we do is we need to come up with a list of these groups. And it turns out that the same list we come up with for reactivities, we can modify in order to tell us whether the group's going to add ortho, para, or meta. But we also need to define then an electron donating group, an electron withdrawing group, and which groups are which. Which groups are donating, which groups are withdrawing. Because the ultimate goal here is this: benzene reacting with an electrophile, the benzene is the nucleophile. So anything I can do to push electron density into the ring is going to make the reaction faster. So an electron donating group that's pushing electron density into the ring is going to make it react faster. Anything that pulls electron density out is going to make the benzene ring react slower. Because it's going to have less electron density. So I need to know what my electron donating and my electron withdrawing groups are. They go by another name usually, or synonymously. Electron donating groups, since they make the reaction go faster, are called activating groups. And electron withdrawing groups that make the benzene ring react slower are called deactivating groups. And with one exception, the electron donating, activating, and electron withdrawing, deactivating groups, that's how we break down whether it's ortho para directing or whether it's meta directing. But there is one exception. There is an electron withdrawing deactivating group that is an ortho para director. Is anybody bored because they read all this? No. Some of it didn't make sense. So what we need to do now is we need to make a chart. We need to go from 1 We need to go from 1 to 10. The groups that cause the benzene ring to react fastest in order down to the group that would cause it to react the slowest. And so we need to make that list. The first 4 groups are going to push electron density in, so they are going to be activating groups. Of course, benzene itself is kind of the baseline, so that's number 5. And then 6 through 10 are going to be deactivating groups. So this is the chart we need. You need to know this chart from number 1 to number 10. So number 1, if there's a nitrogen attached to the ring, that's the most activating. That causes the benzene ring to react the fastest. And number 2, when there's an oxygen group attached to the benzene ring. And this is going to be sort of my simplified list, because there's also a more complicated list than this, but this group from number 1 to 10 will work for us. Right. Nitrogen, most electronegative, most activating. Oxygen, second most activating. Back when we had graduate students in our chemistry program, they and undergraduates were teaching assistants, so one was adding iodine to benzene rings by some novel reaction. And she asked me in lab, she said, what's the most activating benzene ring that we have? And I said, well, if you add a nitrogen group to it, that's, going to be really activating and really reactive. So then, like a couple days later, I said, so did you try that reaction? And she goes, oh yeah, it was so active that it just kind of sprayed the stuff onto the top of the hood. It was in our old science building that's now a parking lot. And so the hoods were pretty crappy to begin with, but that didn't help them. And so she's like, yeah, it was pretty active. So nitrogen number 1, oxygen number 2. Number 3, alkyl group. Sorry. Number 3, another benzene ring. Number 4, alkyl group. So nitrogen, oxygen, another benzene ring, and an alkyl group. Number 1 through 4, anytime those are attached to a ring, they will go faster. That's verified by experiment and by kinetics. Then we have benzene. Number 6, now deactivating halogen. Number 7, any carbonyl group. Number 8, C triple bond N. Number 9, NO2. Number 10, when you have 4 alkyl groups attached to a nitrogen, that nitrogen has a permanent positive charge. Put a positive charged nitrogen species on a benzene ring. It is the least reactive ring, and actually there's many textbooks that say that it will not react in electrophilic aromatic substitution. So this, you need to know these groups from number 1 to number 10 in order. Now, I'm kind of at a conundrum here because we could spend the rest of this talking about why, or we can just accept this fact, this order, and we can go on and do reactions and apply. So I think what we're going to do today is we're going to apply this chart. Now, last thing, and then we'll take a break, and then we'll come back, and then we'll figure out reactions. Then if you're like, well, I really want to know why these do what they do, I would refer you to some outstanding video lectures that are in today's folder. Some more or less outstanding than others, but where I go through this. But right now I think we're just going to accept that. Here's what else we're going to accept. We're going to accept that all the activating groups direct the electrophile ortho and para to themselves. And all but one deactivating group will direct meta to itself. And the exception is that halogens, while they are deactivating, are ortho-para directors. So they will direct the electrophile to the ortho and para positions relative to each other. And that's the next thing we'll do is we'll write those products. And there's a reason why you have to know this chart, because this chart's going to be important when I have not one group on the ring, but when I have 2 groups on the ring and I'm trying to add a third, who's going to direct? Okay. So let's take a break, and then we'll start back up at like 10:32. And then we'll apply this chart and start thinking about how to make different benzene rings. Okay. So here's our list. So what does it mean to be an ortho-para director? What does it mean to be a meta director? Well, so we have a long list of how to add these different groups to the ring. And the reason that I showed you the diazonium reactions is because the diazonium reactions will allow us to add the OH group. The reduction of the nitro allows us to add the NH group. And then the diazonium salts allow us to add a C at triple bond N, and maybe other ways to make the halogen. So, you know, if I'm looking at this list, I need to be able to make all the groups on the list, which I can, and which we'll go through the various possibilities. So, first step is add the first group. And then once I add that group, the question is, what happens when I add the next electrophile? So let's take something, I don't know, let's take something straightforward, like let's take methyl chloride with aluminum trichloride. What am I going to add to that benzene ring? Methyl. Does it matter where? No. But now let's add HNO3, H2SO4 to this methyl benzene, which is called toluene. So I think we used toluene in lab last week. So this is toluene. Right, so what is my final product of that reaction going to be? So let me ask you to write this on your board. And what do I need to know to answer this question? If you already know what you need to know, then you're just whipping out the answer. But if you're kind of like, I don't know, what do I need to know to answer this question? What do I need to know? Okay, the position. So what position? But before I even know the position, what do I need to know? What I'm adding to the ring. So I would encourage you, and again, if you have your own system, don't let me mess with it, but I would strongly encourage that, first of all, what am I adding? And then secondly, where am I adding it? So I'm adding an NO2 plus because that's what these reagents say. So now, write the product or products that you would get. Bless you. Okay? 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 You don't need to plus charge. So, okay? Have I seen everybody's? They would be the same product. It doesn't matter. It's your first answer and that answer are the same product. Okay? Okay, so here's what I saw with a small group. Here are the answers that I saw. I saw ortho, meta, and para products. And you guys got them all. Collectively, you gave me all the possible answers. Now you might say, okay, so putting the nitro group ortho, I could also put the nitro group here and end up with the same product. Meta, I could also put the nitro group there and have the same product, and there's only one para product. You changed your answer? You changed your answer. Okay. Well, let's now we've got to figure out what the major product was. So I just gave you you guys gave yourself the possibilities, right? You just made this a multiple choice question. So we basically, if I'm writing this as a multiple choice question, what I would say is, I would say, here are all the possibilities. A, B, and C, ortho, meta, para. Now, what we find experimentally is that activating groups and halogens add both ortho and para. So you get both sets of groups. Actually, the best way to describe it would be you get no meta. You get no meta substitution. And when you have a deactivating group, you get meta, you don't get any ortho-para products. Now, this is not a forbidden set of products. In other words, you could do a reaction with an activating group, and it could give meta products. Those won't be the major products. Okay? So really, our choices are not necessarily A, B, and C. It's A, B, C, and then D, which would be A and C. So those would be your four choices. So A only, B only, C only, or A and B. Or A and C, which would be D. Now, humor me and write down the letter of what you think the major product will be. A, B, C, or D. And I'm going to tally them. Okay? Okay, I think I got, how many do I have? I've got 8, 9, I need one more. I need one more after that. Okay, so we got 9 to 1, B to C. Okay. Now, I've been doing this a long time. I don't know how many times I've said this summer, but I've been doing it a long time. There's a reason why I asked this question first. Because I would like to destroy a misconception that people sometimes have when they start these problems. Okay. Who is directing? It's a rhetorical question. The group that is on the ring is going to be the director. That is the group that directs. And it tells the electrophile where to go. Oh, didn't I kind of say that though? Well, we have it now. So It's the group on the ring that's the director. So when I have this list, when I go back and I have this list of things, of groups, these are groups that are already on the ring. And the group that's already on the ring is going to direct the electrophile where to go. And your choices are ortho and para, or meta. And that was your first answer, right? Because you had both of them the first time, and then you changed it. So you might want to go with your gut. Oh. Okay, then don't check your gut. So, given that clarification then, what would be the major product? D. So, the director is on the ring. The group does not self-direct. The group that's on the ring is going to be the director. So when I do this problem, there are two steps. Number one, what's my electrophile? But number two, bless you, what kind of group is on the ring and what kind of director is it? And then I put the electrophile into the position or positions that the group is directing it to, that the group already on the ring is directing it to. So in this case, the major product would be A and C.
When you do records O and P, how do you determine which more of that product?
Well, I'm not concerned about whether I get more ortho and para products, but more ortho or para products. We can basically. I mean, what would be your gut instinct? What would be your gut instinct in terms of what do you think you get more of, ortho or para? Or you don't have a gut instinct? You said para? Why? Okay, as far apart as possible, which brings into the equation sterics. So I would expect to get more para than ortho, based on sterics. But what I'm going to ask you to do is, if it's an ortho-para director, I'm going to ask you to write both the ortho and para products. Now, if the electrophile is too big, and the group on the ring is too big, you're going to load the system to automatically be mostly para. Right? Because then you're loading the sterics of either the electrophile trying to add, a large electrophile trying to add that's sterics, or the group that's on there is sterically hindered. So if it's ortho-para, you're going to probably push, in those situations, more to the para. But I'm just going to ask you to write both ortho and para. And then if we get a little bit more into this, we would say, oh, well, I'm going to get like 100% para product. But at this point, it's just ortho and para or meta. I will invoke sterics here in a minute. Right? So, let's do another. Let's see. Let's add a BR2 FeBr3. And then let's add a Cl C double bond CH3 with an aluminum trichloride. So why don't you go ahead and write the final product on your board. Okay. 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 So you might want the pair. Okay. Okay. So remember, so if something is ortho and para directing, you're going to write both products, both the ortho and the para products. Okay. Not going to hold it up for me to see. Okay. Right, so the first thing we add is a bromine. The second thing I'm going to be adding is the C double bond O CH3 with the plus charge. And where is that group going to go? It's going to go ortho and para. So I'm going to get the ortho addition for the ortho product, and then I'm going to get the para product. And again, I'm going to ask you to write both products, although we probably expect to clearly get, we would expect to get more para product than ortho. But those are, we're going to get ortho and para products. We're going to get no meta. Okay. All right. So you got to know what you're adding, and you have to know what is directing. So everybody's kind of with me here? Again, hopefully nobody's too terribly bored. All right, so let's make it more complicated. Let's make it more complicated by doing this. I'm going to start with toluene, and I'm going to add nitric and sulfuric acid to it. What's my product going to look like? What am I adding? I'm adding an NO2 plus, and where am I adding it? Ortho and para to the methyl group. the methyl directs. And the methyl's an ortho para director, so it's going to direct the NO2 ortho and para to itself. Remember, the nitro group does not self-direct. The methyl group is directing. All right, so I want to add another nitro group. So I want to add another HNO3, H2SO4 to the ortho nitro toluene. So what happens when two groups go on the ring? Well, that's a good question. Who is directing? Or maybe here's the possibilities. The possibilities are that both of these groups direct to the same positions. And if that's the case, if they both direct to the same positions, that's where the group's going to go. Okay? Is that the case for the ortho-nitro-toluene? Well, where's the methyl group directing? Ortho and para to itself. Where's the nitro group directing? Meta to itself. And meta to itself is the exact same two positions. Now, if there's already a group on the ring, you can't replace that group. So in this case, both groups are directing to the same positions, the same two positions. So my final products are going to be, first, I'm going to add a nitro group here. And in the second product, I'm going to add my nitro group here. Because those two groups directed to the same position. No. Well, yes, but it doesn't matter. Because they're both pointing to the same place. Well, that's the next question. So I was kind of hoping the next one, they'd be pointing in opposite directions, but they don't, right? Methyl directs ortho to itself, nitro directs meta to itself, and so in this case, if I add a second HNO3, H2SO4 to this, then I'm going to end up with a nitro group on either one of those two positions, but that's the same product. Those would all be 1, 2, 4 tri-substituted. So whether it adds to the left or right in the ortho position to the methyl group, I get the same product. Blush. So let's finish this out, and then we'll go to the opposite, what happens if they're pointing in opposite directions, because I want to add a third nitro group to this. If I add a third nitro group to any of these molecules, I'm going to get the same product. So the molecule, so this one, the nitro groups are directing meta, the methyl group's directing now para because there's ortho groups are already there. And so for this one, I'm going to end up putting the methyl group here, and I'm going to end up with 3 nitro groups at those positions. And that would be the same product if I added another nitro group to the middle product here. I'm going to end up with the same product, and if I added another nitro group to this one, I'm going to end up in the same position. So I end up with the same product. All I have to do is nitrate this toluene 3 times. So I'm going to end up with this molecule. So I'm going to trinitrate this toluene. Does anybody know what this is? It is trinitro toluene. So it's TNT. Which is different than nitroglycerin. I think dynamite is nitroglycerin. But you have to take the nitroglycerin, you got to put it in clay in order to make the sticks. That's how Alfred Nobel did it. TNT is a whole other beast. No, that's the point. The point was to get to that. So to make TNT, this is how you would do it. Now there's a reason why this is great on paper and, not great in real life, is because the difficulty in making TNT is every time I put a nitro group on the ring, what have I done? I've made the ring less reactive. And if I make the ring less reactive, how do I get the next nitro group on it? I'm probably going to have to heat it. So there's a fine line here between heating and blowing up. Right? So, and the same thing was true for the nitroglycerin that Alfred Nobel's company made, I think still makes, in the fact that you've got a fine line between heating and detonating. Heating to get the reaction to go. So it's kind of like if you're making maple syrup from the sap and you have to boil it down. The people that do that sit on three-legged stools so that if they fall asleep, they end up hitting the floor and waking back up again so you don't burn the whole place down. The same thing would be kind of true here. You'd have to go very carefully in terms of heating. And Alfred Nobel, a lot of family members were blown up. And so at the end of his life, that's why he gave all of his money to the Nobel and founded the Nobel, because they lost a lot of family members in the making of the nitroglycerin, which would be just as hard as making TNT. So that's the most famous electrophilic aromatic substitution. And people tried different ones to make different explosives throughout the year, and this is probably the best. In some places in the U.S., there's a lot of TNT in the soil and in the ground, and hopefully it doesn't get into the groundwater. But it's in the soil because there were armaments, during probably World War II. And so there's a lot of it where they were blowing stuff up and it got into the ground. And we'll talk about that because how do you make this, if you got a bunch of TNT, how do you turn it into something that won't explode? And we'll talk about that tomorrow or Thursday. So this is an illustration of what happens when the groups point to the same direction, which is the easiest case. So let's go on to a second case where that's not quite the case. How about I put a bromine here, and I put a, let's see, I'll put a nitro group here. And then let's add a methyl. Let's add a methyl chloride with an AlCl3. Okay? So I want to add a methyl group to this system. And let's call this A and B and C and D. Now, there's a couple rules. There's one rule I have to impose right at the moment is that you cannot add in between two meta groups. If you have two groups that are meta or 1,3, you cannot add in between them because of steric hindrance. So you cannot add to A, because you may think, well, bromine's not that big, and nitro's not that big, and methyl isn't that big. Oh no, they're that big. A bromine is actually the size of a methyl group. So there's steric hindrance for the methyl group to get to the carbon to add to the ring. So you cannot add in between meta groups. You're not allowed to do that. Right, for sterics. So now I've invoked the sterics. So that leaves us with B, C, and D. So where's the nitro group directing? To C. Where is the bromine directing? To B and D. Who wins? Maybe not. Who directs? What? Nope. That's not that has nothing to do with it. They're both on the ring. BR? Alex? We got to use the list. This is why we have to know the list from number 1 to number 10. I guess the question is, that's one possibility, the BR because it's higher on the list, or the NO2 because it's lower on the list. Well, let's think about, what does the list represent? Who's activating, who's making the ring react faster? So BR wins, because it's higher on the list. So that means if the BR wins, then we are going to add the methyl group to the ortho position to the bromine, and then I'm going to add the methyl group to the para position relative to the bromine. And here's an important thing: are those the same product? No, and so those are two different products. What if they were the same? Then you would only need to write it once, or if you wrote it the second time, write like an arrow saying same products. Okay, so I would get these two products as my major product. So when the groups point in different directions, the group higher up on the list wins, which is why you have to know the list. Now, let's see. If I go back to circa 2000, this is the way I used to teach this. And say, okay, if they point in the same direction, that's where it's going to go. If they point opposite direction, the group higher on the list wins. Student, who I still remember the student because they're a physician down at Akron's Children's Hospital, said, do I really need to worry about that, because can't I just jump right to the group that's highest on the list, and that's the one that's going to direct? So I don't have to worry about whether they're directing in the same position or opposite positions, because ultimately the group on the top of the list is going to direct. And it's like, yeah. So we don't have to worry about whether they're directing to the same position or opposite positions, because the group that's highest up on the list is going to do the direction. Right? So I said, that is genius. I'm going to use that from now on.
The group that is higher up on the list is directing to the spot.
No. If it's So any spots that are directed to that already have a group can't be substituted. So that, for instance, okay, let's do this then. Let's take it one step further. Let's add a Cl2 with an FeCl3 to this one. And so where would it go? What would be the products of that reaction, of taking that tri-substituted and now reacting with Cl2? Where's the Cl2 go? And I'll give you 3 choices. It's a choice. I don't know that I'll use it, but it's a choice. So what letter or letters are we going to add the Cl to? Those aren't letters. Those are letters, but they're not A, B, or C. So where should I put the chlorine in the product? The product's going to get a chlorine. So where should the chlorine go? Should it go to A, B, C, or some combination of letters? B? We all in agreement it'll go to B? So in other words, who's directing? Of those 3 groups, who's the highest? Of those 3 groups, which ones are the highest? You're right, CH3. So CH3 is the highest. And so how does it direct? Ortho and para, so it directs to B, and then it's trying to direct para to itself, but there's a group there, so I can't add the chlorine to that group, so that means the chlorine goes to B. Okay, so if there's a group there, you cannot add to it. So all we have to worry about is just finding the group that's the highest on the list. Sometimes in the past, when I start an exam, I'll hand out the list and have you fill it in, and then grade that, and then give you a hopefully correct list. But I wouldn't really assume I'm going to do that, so you need to know the list. As a matter of fact, what's today? Tuesday. So how about we will start class on Thursday with a quiz where you have to write the list. Because, I mean, it's got to go in here, so I should probably do something to kind of get it to go in there, short of a hammer. Okay. So Thursday I'll just give you number 1 through number 10, and you'll write the groups. Oh, and then I'll probably ask you whether they're ortho, para, or meta directors. Right, but if you get the list, the rest of it's a piece of cake. If you remember the one exception. Now, tomorrow, let me show you. Tomorrow we're going to still come back and do some of this, but we're going to do it from the standpoint of, I'm going to give you a benzene ring, and I'm going to say, I would like you to make bless you. I would like you to make something like that. With an NH2. So how would you put steps together in order to make this molecule? Number one, getting the NH2 group on the ring. Number two, getting the ethyl group on the ring, or maybe vice versa. How do you get these two groups on the ring, and then how do you do it in the right order so that they are meta? Because if I look at this, neither one of those two are meta groups, or meta directors. So how do they get on their meta? But here's what I would like you to do for tomorrow. In the Wednesday folder, because I've got basically, there's the things for tomorrow. We're kind of in a position where each day is its own theme. So whatever yesterday's theme was, today's theme is sort of electrophilic aromatic substitutions. Did I make it through all of it? No, but I'll mop it up tomorrow. So for Wednesday, there is, let's see, not Wednesday, August 7th. That'll be here in no time. But Wednesday, there is, you can read through the book, but what I would ask you to do is to look at this, this video on all the different organometallic reactions to add things to benzene rings, because that's going to outline what's in the book. Or you can read the book and take a look at that. But that is going to be the bulk of what we talk about tomorrow. There is aldehydes and ketones, but we're going to start aldehydes and ketones. We probably won't make it through. So we'll pick that up on Thursday when we start talking about aldehydes and ketones, and that'll be the theme of the day. So tomorrow's theme will be all these reactions that are there are basically still benzene ring reactions. So I would ask you to look at that, and if you, as you're doing that, write down any questions that you have. And then tomorrow we'll talk about, we'll incorporate these after your questions. We'll incorporate these reactions into how do I go from benzene to another molecule with 1, 2, or 3 groups on it. And if you want, there are mucho amounts of practice problems, set 1, set 2, set 3, all the way down to set 5. Some of these are like out of control, because you have to, because then there's some where, you know, you have to do 2 different diazonium salt reactions to add the groups. And remember, diazonium salt is if you have to use a diazonium salt, that is a guaranteed 4 steps. And so you're going to have to remember, I do this to get to diazonium salt, and then I do this to get to the next group. Okay, so that's what I'm going to ask you to look at. That file is, you download that file to your computer. It should open up in Adobe Reader, the newest Adobe Reader, but you also have to make sure you have Flash on your computer, installed on your computer, and then it should read. So there is a video PDF file. This is a video PDF file. So when you click on it, it will give you, when you click on it, it will take you probably to my Evernote account. And then when you click on the Evernote file, it will download it to the computer. Once it downloads it to the computer, if you're in Windows, or if you're in whatever your browser is, if you try and open it up here, I do not believe that it will necessarily give you the option to listen to it. How are you opening in 2 minutes? Oh, unacceptable. So then you can go to your Adobe Reader. You can go to your Adobe Reader, and then you can open it up, and then it'll play like a normal video. If you have issues, you can email me, but that's what I would like you to do for tomorrow so that we can combine everything together. And I will have your exams back to you tomorrow.